Okay, let's see, we'll give ourselves a minute to let people trickle in here, and we are recording, and we should have the closed captioning on, I think. Okay, I'm gonna wait one more minute and then I think we'll go ahead and get started.
And you can still see my screen, right?
Mm-hmm. That's perfect. Okay, well, let's go ahead and get started. So today is officially Unit 1 of ROSES 2021, and we are going to be talking about metadata with Dr. Emily Wolin. So before I introduce Dr. Wolin, I just want to give a reminder that this session will be recorded, and we hope to upload the link to the video on YouTube within 24 hours. And the notebook for this session that Emily will be talking through has been uploaded to the GitHub, so you should be able to pull from the repository, and then you'll have the notebook on your machine locally, and you can work through the video. And then we do have a Q&A box, so throughout Dr. Wolin's lecture, you can ask any questions in the Q&A box, and I will verbalize them, and then she'll do her best to answer your questions. So don't hesitate to ask any questions that you may have, and we will hope to get them answered. Okay, so Dr. Wolin is a seismic network manager at the USGS Albuquerque Seismological Laboratory. She has a PhD from Northwestern University, and she was a lecturer in ROSES 2020. Her lecture was awesome, and I think really useful for all of our students, and I hope it will be useful for you all as well. So here we go.
Alrighty, well, thank you for the introduction, Francisca. I'm really glad to be back for ROSES 2021. Last year was a great experience, and I hope that that this year turns out the same. So yeah, nice to meet you all. I'm really glad that you're here and want to learn about metadata and instrumentation. I like to, this is the foundation of seismology. You need to know about your instruments. You need to know how to obtain accurate measurements from them in order to do pretty much any branch of seismology. I scrolled through the introductions. It looks like we have a wonderful range of subdisciplines represented here. And so I hope that everyone will be able to take away something valuable from this lecture today. So I'm going to try to talk for about an hour or less, maybe jump over to the lab notebook a little bit in the lecture to check it out, and then we'll turn you loose on the lab. The lab is pretty open-ended. It's meant for you to be able to experiment and with different processing parameters and see how it affects your data. So yeah, we'll do the lecture first, a little bit of notebook work, and then turn you loose on the lab. So here we go. In the Slack chat this morning, about an hour ago, if you saw it, I asked you to think about, for your research, to kind of get you in a mindset where this lecture is going to be helpful for you, just think about quickly, what's the frequency content of the signals you work with? What's their amplitude? How accurately for your results do you need to measure the amplitude of a signal? And how accurately do you need to measure or know the phase of a signal? So a couple of different examples might be, oh, I'm doing upper mantle tomography using teleseismic surface waves from magnitude 6 and above quakes, looking at long periods. My signals are pretty large relative to ambient noise in that band. I'm using mostly vertical component data. So the phase is really important. If you're doing, say, attenuation tomography, the amplitude might be really important for you as well. If you are doing strong motion seismology, you're looking at really large signals, right? Signals of, maybe 1 G of acceleration from nearby earthquakes, using frequencies maybe down to 0.1 Hertz, but mostly higher frequency stuff. Things like that. You might be locating earthquakes using body waves in kind of the 1 Hertz range for teleseisms, big range of signal to noise ratios, and you really need to have good timing on that data. So there's a very wide variety of the types of signals we record and the what you need to know about the instrument and indeed the instrument itself that are used in these studies. All right, so here we go. We'll go ahead and get started. I want to first acknowledge that this material, a good chunk of it was originally developed as part of the instrument response functions tutorial for the USRA data processing course. So that was developed by Bob Woodward and Suzanne Vanderlee. And I have taken that and built it into the lecture you're seeing today, but very grateful to those two for getting this started and organizing training courses like this that have been a really important part of my development as a seismologist. Okay, so I like to start off every lecture with take-home points in case your internet cuts out or you have to leave, or you stop paying attention because goodness knows it's hard to pay attention to all these video lectures these days. So here's what I would like you to take away from today. Instrument responses look complicated, but you don't have to treat them like a black box. All an instrument response is it's a description of the process of taking a physical ground motion from an earthquake or any other type of ground vibration and converting it to a digital signal that you get from your favorite data management center, say IRIS or Orpheus or something like that. When you're removing an instrument response, you need to choose your processing parameters carefully. And this is going to vary depending on your specific application, right? So today you're not going to get the ideal set of parameters for exactly your application, but you're going to play around with a lab notebook that will help you kind of visualize how changing these parameters affects the outcome. You're going to learn a little bit more about the capabilities and limitations of various kinds of seismic instrumentation. And as a final note, there's a big body of seismic instrumentation literature, but it's very often written in a way that's kind of dense and hard to read if you're not a specialist. So I want to put myself out there. If you have questions about this topic, please feel free to contact me. I'll do my best to answer your questions about metadata, instrumentation, all these kind of things. All right, so a little bit more context. Why do you need to think about instrumentation and metadata? Well, one really important reason is that seismology has this fantastic history of sharing data freely, right? You can, many experiments have produce publicly available data. National networks, national seismic networks like the one I run, regional seismic networks, we make our data free to everyone to look at. So that means that you can get data very easily from a very wide variety of stations, very wide variety of instruments. But depending on what you're trying to do with that data for monitoring or research, it's important to make sure you're choosing the right tool for the job. So the right kinds of equipment, right kinds of stations that are producing the data that you need. Very often in your science, you're going to need to use metadata to convert the raw signal you get in terms of digital counts from, say, IRIS, back to physical units of ground motion, right? Whether that's displacement or velocity or acceleration. And in doing so, or even in any study, it's really important to understand what your instruments can do and what they cannot do for you so that you're choosing appropriate data. All right, so here's an example of 3 different types of seismic stations that you may have seen before or have seen similar stations. So the one on the left is the Global Seismographic Network, the GSN, right? This is the II network, the IU network, other various federated stations participating in the GSN. And the goal of these stations is to provide extremely high quality, long-term observations for research and monitoring. And they have a really special emphasis on long period data. And when I say long periods, I usually mean periods about 100 seconds and above, right? That's a pet peeve of mine. We'll go over that later. Always say what you mean when you say long period or high frequency or something like that. But anyways, and this is a network designed to provide global coverage for these mostly long period data. It's also a really good backbone network for global earthquake monitoring. So this is also used for things like tsunami warning, for example. So this network is equipped with very often broadband sensors, sometimes multiple broadband sensors at one site. Here you can see there's a borehole instrument. This is a site in Antarctica. This borehole is very, very deep, tens or maybe 100 meters or more. And this instrument is being lowered down there so that it has a very stable environment and can produce really high quality long period data. All right, I had a request to go in full screen. Let me see if I can do that. Okay, hopefully that's better. All right, the middle column here is part of the ANSS backbone network. So this is the regional or the National Seismic Monitoring Network for the United States. So the goal of this network is to monitor magnitude 2.5 or greater earthquakes inside the United States. The network is designed in such a way to provide mostly uniform coverage across the lower 48 states, filling gaps in between where we have denser regional networks like in, say, Missouri or California or the Pacific Northwest. And you can see here, this fault is set up a little bit differently. We have a barrel that's been buried in concrete. So not our super deep borehole. It's got different types of instrumentation here. We have both a strong motion instrument and a broadband instrument co-located so that we can record a wide range of ground motion. And then finally, a third type of station that many of you may be familiar with is a portable deployment, right? So this is something that you would leave out for only a couple of years. In this case, this is a pool of portable instrumentation that I manage that is mostly designed to respond very quickly within a day and a half to significant earthquakes within the US. So we want to be able to get this out quickly, install it as fast as we can so that we can record strong ground motions and also provide data for studies of very small events to help get better resolution on fault parameters. And we want to densify coverage between whatever existing regional networks might be in the area. So we have a Pelican case here. All of the equipment's in here except for our 2 seismometers that are buried in very shallow vaults just below the surface, right? Because we're sitting right on top of the signals, we're trying to record these earthquakes. You know, we don't have the time or money to put in a borehole site. Even this regional site would be overkill. This does just fine for the kind of data we want to record. And every single station you see here has slightly different instrumentation so that it meets its monitoring goals. Okay, so let's get started talking about what exactly is an instrument response anyway. So in order to end up with the data that you get from IRIS, hopefully you can see my cursor over here. You get waveforms and metadata from your favorite data management center. But it all begins with an actual ground motion, right? An earthquake happens, a truck drives by, a cow stands on top of your station, you jump up and down next to it, whatever, something makes the ground shake. You have a seismometer that has a mechanical electrical response to that ground motion, right? That seismometer puts out a signal, an analog signal, that's a certain, a voltage that is then recorded by a digitizer or data logger. So it takes, your analog voltage, expresses it in terms of counts, digital counts. And then this is the part we won't talk about today. So this part is the instrument response. Everything beyond that is a big part of my job as a network manager, making sure we actually get the data through our communication systems, sending it off to Iris, publishing metadata, stuff like that. But I want to focus on this first step here. So going from actual ground motion to the digital signal that's output by the digitizer. Another way you can think of this, the seismogram that you get from, once again, your favorite data management center is a convolution of three different things. We have the source itself. So I would normally think of this as an earthquake. Of course, it could be microseisms, could be ambient noise produced by humans, anything like that, a hammer blow on the ground. It interacts with Earth's structure that modifies your signal. And then it's recorded finally by the instrument, right? So in my mind, when I'm thinking about metadata, this is some arbitrary signal that comes in. It goes through a linear system with a known response. And then the signal that you get out is the convolution of these two things, your input signal at your seismic recording site and the response of that instrument. So most of the time, you want to remove the instrument response so that you can actually get at your source or your structure or both. All right. So another way to say, to think about this, an instrument response is what you get if you put in an impulse into your linear system. So if you put in an impulse to this system, you get out what's known as an impulse response if you're working in the time domain, or a transfer function if you're working in the frequency domain. I am often pretty loose about using one of those two, right? So you put this in, and this is what you get out. And it's very common to represent an instrument response as two plots. So one is the amplitude response with frequency or period, and one is the phase response with frequency or period. And in this plot, I have examples from two different stations, two different instruments. You can see that one of them has a flat response to a broader range of frequencies with a corner up here at probably a couple hundred seconds. And then another one has a very different response with a narrower flat band and a higher corner frequency. Okay, so you can go ahead and run the first 3 cells of the lab notebook if you have it up and available. I'll switch over to that in a moment. But all we're going to do here is obtain and plot a response object using obspi. So here's the code that will do that. It should already be in the notebook for you. And we're going to go ahead and grab metadata from 2 different stations. These are both at Iris. For the rest of this, I'm going to be assuming that everyone has done the obspi lab. And if you haven't, then you'll have an example to get you started on grabbing some metadata. So I'm grabbing data from Iris. I am specifying a time that I want my metadata for, right? Because metadata at a station can change over time if you change out the instruments or digitizers or other equipment. So yeah, then I'm just using this Iris client to grab data from one station and then a second one and plotting the response, which you can see over here. And then finally, OBSPI will also write this out for you as a, I'm choosing here to use a station XML file, which is a nice human readable format for metadata. So I'm going to pause for probably just a minute or two and let folks go ahead and run this. Please put your questions in the chat box or the Q&A, whichever Francisca has told you to do, and we'll help you out and answer any questions. So let's do 2 minutes. Are there any questions so far?
So there is, it looks like there is a question. I don't know if you can see that question, Emily, that can we use this code for our data without the client command?
Okay, yeah, good question. So if you have a local copy of your metadata, you know, as a response or a data list or an XML, yes, you can do that. So OBSPI has a module called read_inventory. And you can read, you know, if you have a local copy of it on then yeah, you can just read that in using that command. So let me show this, and I know it's tiny on the screen, but I'll try to make it bigger. Okay, so I've got my roses environment, and because I've run this notebook a couple of times, I have a file called inventory.xml. So I'll start up IPython here. Import OBSPI. And then I'm going to say my inventory is obspi.read_inventory. And then I'll give the file name. So in this case, it's just inventory.xml. And OBSPI can normally kind of auto detect the format of your metadata. But if it can't, then there are options to specify what format it's in if it's having trouble. And then if I print my inventory, there you go. I have metadata for those 2 channels that I had requested earlier using the notebook. All right. Let's see here. I see a couple of questions. So can we save the output file? It depends on your needs. I generally like to do it. I like to request my waveforms and my metadata once, and then have an option in my script that would say, look to see if I have those files already, just so I avoid, you know, that processing time of having to make the request to a data center, grab the data, write it out, especially since we're all working from home, or many of us are working from home now. It takes a lot of time. I don't have the fastest internet in the world. So, but yeah, you know, it depends on your needs. And then a second question, what kinds of seismometers are used in general for portable stations? And are nodal seismometers used in portable stations? So I'll answer for the portable response program that I run. Our mission is to support the National Earthquake Information Center in Golden, Colorado, also operated by the USGS. And the kinds of data that they want, we have 2 sensors in these rapid response kits. We have a Trillium Compact, which is a broadband with a little bit higher self noise than a typical broadband. We'll talk about that later on in the lecture. But it gets, you know, it's a broadband instrument, so we can do a lot of things with it. And we also have a strong motion accelerometer to record strong ground motions to support the National Seismic Hazard Program as well, to provide studies for, say, ground motion studies. Okay. Excellent question that I'm going to address later from Hamza. Do two stations with the same sensor and data logger have the same metadata? Does it include information like orientation? So short answer is orientation is very, very important. And yeah, we'll talk about that a little bit later, but thank you for your question. And please ask again if you don't feel like I've answered it by the end of the lecture. Okay, so by now, folks who are running the notebook should have been able to produce this plot. I did want to point out one extra thing you can do that I didn't have in the notebook that's on GitHub. So the inventory object has this plot response method, and that gives you a response plot that amplitude and phase with frequency. But it also has just a plot method, and if you call that, then you get an actual map, assuming you have CartoPy or basemap installed, of where your stations are located on Earth. So this can be a nice tool to use just for your own information, making sure you're getting the stations that you expected to see. Okay. So I'm going to hop back over to the slides, and we will come back to the notebook later on for the lecture, or sorry, for the lab. Okay, and I'm going to keep this on not full screen for just a moment because I'm going to look through a text file here in a second. Okay, so metadata formats. There are a lot of different ones out there. The one that you requested just now in this exercise is in station XML. You've probably heard of the seed format, which you can get as a data list seed that contains only metadata, or a full seed volume that contains both metadata and waveforms. You may have worked mostly with SAC POL0 files. These are all different formats that have different applications. In general, the Iris DMC, when they ingest the metadata that my networks produce, they're moving towards hosting things in station XML because it's human readable. We'll see that in a minute. It's very flexible. You can put a lot of information about equipment in there, assuming the operator wants to supply or publish it. So let's go ahead and look at a station XML file. So you can open that inventory.xml file in your preferred text editor, and we'll go through and look at a couple different stages of the response. All right, so this is human readable, right? It's not a binary file like data lists, but it is an XML file. So there's a lot of tags describing what everything is. So I can find out where and how and when I got this data. And then here's where we get into the information about the actual station. So we have a network code. This network has a digital object identifier that you can cite when you use data for publications and studies. And then the station that I requested is PLID. It has a certain start date. We have a station latitude and longitude and elevation. The name of the site, this is the station in Idaho, the United States. And it has quite a number of channels, but we've only requested metadata for one. So we requested the BHZ channel, broadband vertical component channel. And this, we gave it a start time of 2020. So our request grabbed the closest open epoch, which started in 2016. It's currently open. The data is freely available. And yeah, you get a bunch of information about your channel. So this is continuously recorded. It's a geophysical instrument. It tells you the sample rate of your data. Provides information about the sensor. So here we have its velocity sensor. It's a broadband. It's a Nanometrics Trillium 120 PA. You have its serial number in there. The digitizer is a RefTech 130. And then we get to the response. So depending on what level of response you request in OBSPI, you might not get this response. It's important to specify that you want response information. Okay, so we have a couple of different stages here. We'll talk about those in just a second. Talk about them more, but we have stage 1, which is a POL0 stage. we list out all of our poles and zeros here. We have a decimation stage. We have a stage that basically just specifies the frequency at which our sensitivity is described. And then we have a bunch of different stages that describe what are called FIR filters. Again, we'll be there in just a second, but these are filters in the digitizer that are applied during the digitization process to avoid anti-aliasing. And they have just these huge long lists of coefficients very often. This is fairly straightforward. Depending on your digitizer, you might have a number of these things applied. You can see we're at stage 10 up here. And again, this looks messy. We have this huge list of coefficients, hundreds of coefficients, but all this is saying is this is what is happening inside that seismometer and digitizer to get from a ground motion input to the digital signal that you can request from a data center. That's all that's going on here. Yeah, big long list of coefficients. So there you go. You can see our second station starts here, GS network, station PR01. Okay. So I'll head back to the lecture now. So yeah, we found kind of three different stages of the response. We had a seismometer, right? So this is conversion from the ground motion to volts. It's usually specified in poles and zeros, and a gain, a digitizer response converting from volts to counts, and then a long list of finite impulse response for filters that describe the anti-aliasing filters applied by the digitizer. So one question that you might be asking yourself is, how do I tell if a response is like what response units is specified in? You can actually go to your station XML, for example, and tell you. So most of the time, a broadband sensor, its response will be specified in terms of velocity. So if you apply that response, it'll come out in units of velocity. For an accelerometer, it'll come out in response of acceleration, but not always. There's always flunky cases out there. So if something doesn't look right, check the response. I have seen probably one of the strangest examples, an accelerometer response that if you applied it, converted to units of displacement. So there was a lot of long period stuff in there that didn't look quite right. So always good to double check, make sure you're getting correct metadata. Okay, and then yeah, as you saw in the lab, different types of seismometers will have slightly different responses. So here's an example for 3 different seismometers that were used extensively in the transportable array, part of which was adopted by the USGS as the N4 network, which I operate now. So the seismometer response, you can see these 3 instruments have one of them has a longer period corner frequency than the others. And they all have a slightly different response at high frequencies, around 10 Hertz here. So these are just 3 sensors, Geralt 3T, an STS2, and a Trillium 240. Iris has a beautiful, huge nominal response library. So that's responses provided by the instrument manufacturers that you can look at if you need to make metadata for a station or an instrument that you don't have a response for. So I strongly encourage you to check it out. There are hundreds of sensors, hundreds of digitizers in that library. Okay, so going back to our model from before, we have some input signal of ground motion to our sensor, and that's what we get out is a convolution of that input signal and the instrument response. So if you want to go back to the ground motion from your raw data, then you just do a deconvolution, thinking in the time domain, or a division if we're thinking in the frequency domain, right? And so you can think of that, we have that response before, and then you just flip it upside down and multiply by that. So I apologize that I didn't get to go through the tutorial on OBSPI. This was an example that was done last year. So I hope that you've been able to do this, but if not, you'll get to see it in the lab. So here's an example, right? Deconvolving the instrument response is division in the frequency domain. So on the right side of the screen here, we have our time series. On the left side, we have an amplitude spectrum, right? So this is amplitude versus frequency. And here's what the raw spectrum of our data looks like in blue before we do any deconvolution. In the second row down, you can see we've done a little bit of pre-filtering on the data, and our instrument response is plotted. So this is a broadband seismometer. And I can look at that and say it because it's got a corner frequency of about 100 seconds or more. Nice broad band, flat band here with frequency. And then to do the deconvolution of the instrument response, you can see that OpSpy makes this nice plot for us that turns the instrument response upside down to represent that division. And here's our output seismogram. Doesn't look too different from the original, but you can see that the units over here have changed, right? So instead of a few, like several million counts, are now in units of ground motion, probably in meters per second. Okay, this was a large earthquake recorded a couple 100 kilometers away on this site. Okay. All right, so one thing you might be looking at here, you might be familiar with the idea of the corner frequency of a seismometer, especially if you're shopping for instruments. Very often, oh, do you want an instrument with a 30-second corner or a 60-second or 120-second corner? These are options that you can most of the time or many times select, or the manufacturers will have on their data sheets. But there's also a certain roll-off at high frequencies here. And this is important to be aware of, especially if you are working at frequencies that are close to your Nyquist frequency, right? So what exactly is going on here? This corner is shaped by the electrical and mechanical properties of the seismometer itself, so the actual instrument. This roll-off, those are those anti-aliasing filters in the digitizer that I mentioned a moment ago. So what's happening here is this part of the process, right? This is the analog to digital conversion and the filters that are applied during that process to avoid aliasing high frequency signals into your seismogram. So initially, the seismometer puts out an analog voltage, and let's say we eventually want to get a sample rate of 40 samples per second. Well, in order to do that, the digitizer actually records an extremely high sample rate, thousands of samples per second. And then it applies this filter cascade as it decimates the data down to your desired sample rate to avoid aliasing high frequency signals into your data. So we might start with a high frequencies or a very high sample rate. We apply a digitizer, anti-aliasing filter, another filter, another filter. You saw that RefTech 130 that we were looking at before that had 10 different stages of this process to really knock out all that high frequency stuff. So at the end of it, it's got a combined response, something like this. And if you zoom in on the edge of this, there's actually a little bit of a ripple to this filter, right? We know from basic time series analysis, we can't make it a perfect box. We're always going to have a little bit of an overshoot. But this ripple near the Nyquist frequency is really important to know about and work with if you need really precise amplitude measurements very close to the Nyquist frequency of your data. And this depends on the properties of the digitizer that you're using. So if you really need to know the amplitude within a few percent up in this frequency range, it's important to do a full deconvolution. This response looks flat, from kind of a high level view, but that ripple is there, and it's always there for your from any digitizer. Okay, so quick overview of FIR filters. These are finite impulse response filters. They're used to prevent aliasing in your data. If you are reasonably below the Nyquist frequency, you generally don't have to worry about them too much. But if you're working close to the Nyquist frequency of your data, you may want to be aware of them. They produce a slight ripple near the Nyquist frequency, and they can also produce some ringing, near the Nyquist. So that's important to be aware of if you're, say, trying to pick the onset of high frequency signals. And basically, what can you do about this? It's always going to be there, but now you know about them, so you can be aware of them. And my personal practice, my preference is that if I need high frequency data, I'm not going to look at anything higher than about 50 to 75% of the Nyquist frequency. So for example, if I have data sampled at 40 samples per second, my Nyquist frequency is 20 Hertz. So 50 to 75% of 20 Hertz is 10 to 15 Hertz, right? I want to, for my applications, I want to just avoid that rippling. I don't want to push it because those anti-aliasing filters are not something that is easy to characterize well from my perspective. So I'm just going to say I'm not going to work any higher than 15 Hertz on my 40 samples per second data. And also, when in doubt, just do the full deconvolution, right? A lot of times it's very simple to, say, assume an instrument sensitivity. If you know you're in the flat band of the seismometer, you can just divide by the instrument gain. That's a pretty good approximation for many things. But if you're not sure, get the response, do the full deconvolution. All right. Let's see here.
We have two questions that I think let's try and answer before we move on. So the first question is, are there reasons you deconvolve instrument response in the time domain over the frequency domain or vice versa?
Good question. As far as I know, most of the codes that I've ever used do it in the frequency domain. I think it's just simpler to set up from a programming standpoint. Yeah, I don't think I have a great answer for that. I would say mostly frequency domain, but that's just my experience. I guess if a time domain deconvolution, maybe if you were trying to process data in real time, perhaps that could be a better way to do it. But yeah, that's okay.
Okay, and then the second, we have three questions. The second question is, do transfer functions always refer to the Fourier transform? I've seen metadata for the Laplace transform, which is somewhat confusing.
I think that, so there are different, I guess if you get into the seed manual, it'd say like a response, like if you're looking at like an old school RESP file that is a different format than station XML, it has different kinds of responses or formats that responses can be specified in, and I believe Laplace transforms are one of them. But yeah, it's it can refer to a Laplace transform as well.
Okay, we have one more question and then we'll move on. So this is an interesting question. Do two stations with the same sensor and data logger have the same metadata? Is there a way to include other information such as the orientation?
Yes, there is a way to include orientation information, and that can be very important. I think in this, actually in this FAQs section, I'm going to talk about that. So yeah, I will say in principle, if you have identical instruments and an identical data logger, those response stages that we looked at in that station XML, so the poles and zeros for the sensor, the digitizer gain, and the FIR filters, those should be identical. It can vary slightly on what source of metadata the person is using, right? So if the manufacturer updates their instrument response, you might get slightly different poles and zeros because they're always doing their own testing as well. And even if you have the same digitizer model, say a Q330, digitizers very often have selectable anti-aliasing filters depending on your desired application. So just because it looks like the same digitizer does not mean that the settings for the anti-aliasing filters will be identical. So, and again, that's something that you want to be aware of if you're working near the Nyquist frequency. Less important if you're looking at, say, 10-second period data for a station that's sampling at 20 or 40 or 100 samples per second. Okay. All right, so the next section I want to move on to is a very brief overview of noise sources. Right, so seismometers record earthquakes, but they also record just about anything else that makes the ground shake, as we've seen in the last year. I'll talk about COVID stuff in a minute. But they can record signals from almost anything. Human activity is a huge source of noise on seismometers. So they'll record signals from railroads, from highways, from cars and trucks driving on local roads. If you have an air conditioner running in your house and we're too close to it, that'll make the ground shake. We'll pick it up. Tall objects moving in the wind, they're anchored into the ground, so that'll produce a signal. Resource extraction, oil wells, mining, quarry blasts, rivers, moving over a dam, or if it's a very rocky river, producing a lot of noise. People have actually used seismic instruments to study sediment transport, construction. So in general, this slide is a list of siting criteria for sort of a multi-purpose broadband site that's designed to record, say, regional and teleseismic earthquakes. So you don't want to put it right next to something human-induced that's shaking the ground strongly. You want to have some distance from it because high-frequency energy tends to attenuate quickly. So in general, we try to avoid human sources of noise. But of course, many seismometers are installed in the middle of cities, especially those designed to, say, record strong shaking from earthquakes. Or you might have a seismometer at someone's house, just as a hobbyist, or at a school. Or you might have put a station somewhere and then the town expanded rapidly around it, so it's no longer out in the kind of the suburbs or the rural areas. So I think, and I'm showing a plot made by one of our current students. So this is, the top plot is made by Shiva Subedi. He has this awesome network of Raspberry shakes installed at schools in Nepal. And I'm sure many of you have seen the papers that are coming out with studies like this, but seismometers like these ones in Nepal at schools recorded a drastic drop in high frequency noise as their local area shut down because of COVID restrictions. Here's another plot from Thomas Lecoq in Brussels, again showing that huge drop down in seismic noise once the lockdown was implemented. So this is a slide I made last year. This type of work has now been turned into a really neat paper published in Science. And you can look up that reference and take a look. It's a really neat paper looking at data from a number of different stations around the world, documenting how decreasing human activity changed the noise recorded at these seismometers at high frequencies. And a different source of noise on seismometers are storms in the ocean. So seismometers can record energy from hurricanes. They record energy produced by just standing waves propagating in the ocean. And this is a signal that's so pervasive throughout the Earth. We record it at every single seismic station on Earth. We don't see them on Mars, which is cool. We'd expect this, right? But what this looks like is if you're looking at a frequency spectrum, you see sort of this double peaked shape, sometimes a triple peaked shape if you have one very particularly strong storm here. And this is from a station in Utah. So you can see, looking at a spectrogram from that station, this is where your microseisms are. This is the term used for these signals that are produced by standing waves in the ocean and interacting with coastlines. And you can see that they change in amplitude and frequency throughout time as basically ocean conditions change. Again, the term for these, this sort of study is microseisms. That's also often used. I've heard it in terms of like monitoring oil and gas fields to describe tiny, tiny earthquakes of low magnitude. So again, important to realize it's sort of a double use term. Oh, I see a question. Can electrical sources cause noise like power lines? Yes. Electromagnetic changes, including say like the Northern Lights, if you have a station in Alaska. One of my colleagues, Adam Ringler, has a paper about this. You can actually, the magnetic signals, because seismometers are made of metal, strong electric and magnetic fields can interact with the sensor and produce non-seismic signals. Okay. Another kind of example that we end up seeing it quite a lot at stations that are installed in rural areas. Anything that tilts the surface. And when I say tilts the surface, I don't mean, a large seismic fault scarp popping up. I mean a human or a cow walking by a shallowly installed sensor. Your weight or the weight of the cow will actually cause the ground to deform a little bit and cause a noticeable signal on a seismometer. So here's a couple months of data, and you can see, the time frame where the cattle are in this pasture, and then we confirmed with the landowner that the cattle actually rotate out of that pasture. So here's when they're walking around on top of it, and you can see it gets much, much quieter a few weeks after when there's no cattle nearby. So these surface tilts are mostly seen on the horizontal component. So this is a 3-component site. Vertical is down here, horizontal is up here. And you can see one of our data quality analysts has said, we know there's cattle here. This is fine. We had initially thought the sensor might be broken, but after looking at satellite photos and talking to the landowner, we're like, oh, it's cows. There you go. Other things that can cause surface tilt are the passage of storm fronts, say, or more generally changes in atmospheric pressure that happen relatively fast over the span of a few hours. So this is a really cool study documenting the passage of a storm front. So these are different frames of a radar map, and you can see the red colors here. When the storm front hits the station, you get a long period signal. This is pressure data, but in the seismic data, you also see a change in long period noise as that storm is moving over. So those changes in atmospheric pressure will actually couple into the ground and cause it to tilt and be recorded on your very sensitive broadband seismometer. Okay, any other questions so far? Oh, here we go. What are the frequencies for cow activity? Well, so I would say it depends. So if the cows are moving carefully, you'll see mostly long period tilt. So 20 seconds and longer, 20 to 100 seconds, it'll be sort of a gentle tilt. If they're running over it, and Iris actually has this great animation of a game camera that caught an elk running over a station, you see high frequencies and you can actually see the footfalls of the elk running nearby. So it can be both. It might tilt, or you might actually see like a kind of galloping in your seismogram, and that would be at, say higher frequencies above a Hertz or so. Let's see here.
Then, yeah, we have another question is the noise always in high frequencies, which I think leads really nicely into your slide right here.
Yeah, excellent question. Thank you for asking it. Yeah, so I guess in general, right, when someone says noise, it totally depends on what their idea of a signal is, right? So when I was doing surface wave tomography, I had a very different idea of what noise was than when I am looking at strong motion data, right? Or if you're doing an ambient noise survey in a city, you actually want to be near sources of noise so that you can record them, for example, like cultural activity. So yeah, it totally depends on what's the signal you're looking for and what will interfere with it. So in general, from the perspective of, say, operating a seismic network with a focus on broadband instrumentation, one concept, one set of models you might see very often are the Peterson noise models. And we usually call these the new high noise model, NHNM, and the new low noise model. They're still new, even though they were developed in 1993. But how these models were developed essentially is John Peterson, the former lab chief where I work now, took power spectral densities, right? So this is a spectrum plot expressed in dB with respect to acceleration, still a power spectrum, just different units, power spectral density, with respect to period. And he basically plotted these all up, saying, okay, I know that these are high quality permanent network sites. I'm going to take what I think are quiet time ranges, no earthquakes, no cows, no trains at these sites, and plot them up. And then he drew, kind of lower and upper bounds here and said, all right, these are, empirically the ranges of noise that I expect to see at a well-performing station, right? So this low noise model is the lowest you will ever see noise at a given frequency or period on Earth, except in extremely rare cases, perhaps at high frequencies. This high noise model is sort of the upper bound for where it's useful for global broadband seismology, right? Again, if you have an accelerometer, there are different noise models for that. But these curves mostly represent operational goals for broadband networks. Okay, so building on that, another data quality indicator you might see are these things called PSD PDFs, right? So these are probability density functions of power spectral density curves. And the easy way to think of this is you take a day of data, you slice it up into a bunch of different segments, right? So hour-long segments. You make a power spectral density curve for each, and then you plot them up as a 2D histogram to see where you're most likely to have noise occurring and to see the range of noise that you can observe in a particular time frame. Right. So here's a longer time period of data for a given station. This is HLID in Haley, Idaho. This is part of the US network. And you can see this is power versus period. And you observe a wide range of power levels at different frequencies, right? And this plot has been labeled. If you want to learn more about this, I strongly recommend you read this paper. It's really well written, lays out a clear explanation of these signals. But yeah, you get things like car noise. If you look at the waveforms, you can actually see cars driving by. The high frequencies, you can see body waves arriving. You can see surface waves. But those are low probability signals, right? Kind of the purples and pinks over here. Most of the time, the station is pretty quiet. It's well below a high noise model. It's close to the low noise model here. And you can see kind of these colors at higher probabilities, the greens and blues. The station is mostly recording this noise power at this period for this particular range of time. If you have something like a gap in your data, and it gets zero padded in your processing, that produces higher power that looks flat across the spectrum like this, things like that. So these plots, they're available from Iris Mustang, and this is a tool that I look at pretty much every single day to determine the health of the many stations that we operate at ASL. Okay. A short note about PSDs and PDFs and noise models, and also when you're talking about frequency ranges. So in general, these are the bands that I use when I'm speaking as a network manager focused on broadband instruments. And short periods, high frequencies to me are kind of anything above 1 Hertz, right? This is mostly caused by human activity. And if you want to get away from that noise, you can mitigate it by choosing your site selection or selecting your site carefully, and a little bit on the emplacement. So if you can afford to put in a deep borehole, you get further away from your noise sources on the surface. And that helps knock down the high frequency noise in this band, the sort of 1 to 10 Hertz band. For microseisms, generally 1 to 20 seconds. This is caused, as I mentioned, by storms in the ocean, waves in the ocean. And you can't do much about this unless you go to Mars, right? You're going to see it everywhere on Earth. It'll be stronger near coastlines and weaker in continental interiors. But any power spectral density curve you look at on Earth, you're going to see these microseisms. Finally, long periods, I think of this generally as anything above 20 seconds. And noise in this, right, anything that would tend to overwhelm an earthquake signal is local site response to changes in temperature and pressure. Ground tilt, like I mentioned, if you have large things walking by, or even humans walking by every day, that can produce noise. Big storm fronts moving through will produce long period noise. And this can also, again, be mitigated if you can put your seismometer deeper, if you construct your vault so that it's very stable and well coupled to the ground, it can get a little bit quieter. So long period noise is mostly construction techniques, and also the type of instrument you select. But I'll hammer home this point. If you're talking to a broad range of seismologists, it's really important to define what long period and high frequency actually mean to you, right? For good communication. When I was working on surface wave tomography, high frequency to me meant 0.1 Hertz, because I was only going up to like 20 seconds or so in my waveform fitting. When I talk to strong motion seismologists, 10 seconds, 0.1 Hertz is about as low as they want to go. So, use the terms. It's a nice way of communicating, but make sure you define them clearly so everyone knows what you're talking about. All right. Okay. Any questions so far?
Yeah, we do have one question, and that is, what is the interpretation for noise levels from local nodal stations, PSDs, that cross either the low or high noise boundaries?
Okay, awesome question. Okay, on to the next section. Here we go. Okay.
Oh, and actually there's another question. This is a great question. Since the low noise and low and high noise model curves were defined in 1993, do you think they need to be updated since there's such increased seismic network coverage now?
Yes, okay. Both awesome questions and both leading fantastically into the next section here. So here we go. Thank you guys for the questions. All right, I want to talk a little bit about self-noise for that first question and instrument limitations, because these both play into kind of the floor of the noise, the quietest signals you will record at a site. So the self-noise of a station or a piece of equipment, but from a station perspective, is defined by your choice of instrument and your choice of digitizer. And the self-noise, you can think of it as the smallest resolvable signal that you can record. And this is based on the limits of your instrumentation. So as our first question asker just now pointed out, nodes will have very different self-noise levels than the broadbands that I was just showing you, right? And different instruments can have the same response shape. If you look over on the right here, we have responses for a Trillium 120 seismometer, which is sort of this big dome-shaped seismometer. It's about the size of a bowling ball. And a Trillium compact, same manufacturer, but it's smaller. It's about the size of a can of soda. Weighs much less. And these instruments both have a 120-second corner, right? But if you look at the self-noise level of those two instruments, the T120 or the Trillium 120 volt sensor, this bowling ball, is much closer to the low noise model than the Trillium compact, which is this red curve here. And this is due to the different mechanical and electrical response of those two instruments. So oversimplifying a fair bit, but because that Trillium 120 compact is very small, it has smaller masses, it has higher self noise than this larger volt instrument. So even though the response has the same shape, this is just a noisier instrument at long periods here. You can see it crosses those Peterson noise models, which are flipped around in this plot because it's in terms of frequency instead of period. But you can see that the compact crosses the noise model at a much higher power level than this volt sensor. So if you are, if you're installing a station and you want to record the extremely small signals, the lowest background noise you possibly can, then you would be looking for this volt instrument. If you are, say, like for me, recording very local earthquakes as part of a aftershock response, then a Trillium compact will do you just fine because you're sitting right on top of any signals that you want to be recording. They're going to have a really high amplitude, well above this instrument's self noise. So both are perfectly good instruments, just designed for different purposes. Okay. Yeah, so for frequencies above about a Hertz, we can go ahead and look at the self noise as well. And here's an example from the EarthScope transportable array. So you can go to this Iris Mustang database and get every PSD from every hour recorded by every TA station. This is 71.6 million PSDs. And if you look at the noise floor of that network, there's about 1% of the time, cumulatively over all TA station hours, this recorded noise with an interesting linear shape, or sort of linear with frequency here. So what exactly is this? I was very surprised the first time I saw this. And it turns out that this noise floor for the TA is actually shaped by the self noise of the instrument digitizer combination. Right, so here I'm showing a Q330 digitizer self noise plus the instrument response for a number of different instruments. And it turns out that, yeah, for the types of instruments that were used in the TA and the types of digitizers, this is actually the self noise floor. So in this case, this choice of equipment, instrument and digitizer, actually cannot get close to the Peterson noise models here just because of the properties of the equipment. There are digitizers and sensors that can get out to the Peterson noise models, but they were not used in the TA here. So when assessing the performance of a station here, it's really important to know kind of what equipment is here and the minimum noise floor that it could possibly get, or that it could possibly attain. There you go. Yeah, and again, you can trade off. If you want to record really small signals, you can use a sensor with a higher gain, but then that changes the clipping threshold, right? So you won't be able to record signals that have as high amplitudes as a sensor with a lower gain. All right. Okay. Oh, and I want, just for that question that was asking about reassessing the Peterson noise models. So if you, not to plug my own paper, but to plug my own paper, if you check out this paper, this was in Seismological Research Letters, and I'm happy to email a PDF if you just shoot me an email after this. The first step we did in this study was actually to get GSN PSD PDFs and assess the noise floor. So again, we plotted up all those millions and millions of PSDs and looked at that 0.1 percentile and first percentile. And it turns out that even, 25 years later, the Peterson noise models, at least the low noise model, are still applicable for, it's still pretty much the lowest noise floor you can attain with the data we have now. At a few sites, like say in Antarctica, if you have extremely low noise recording equipment, you can get below the Peterson noise models at say 1 Hertz and above, but these are still very valid noise models to use in a general context for pretty much any station on Earth. All right, so on to that question about noise at nodes, right? So my background, what I mostly worked with in grad school was broadband seismometers, but there's been this really cool broadening of the use of instruments like nodes, for example, right? Or geophones in Raspberry Shakes, right? And if you are used to working with data from permanent broadband sensors, you probably don't think much about self noise, right? If you're working with data recorded by the EarthScope transportable array, looking at earthquake signals, all of your data is going to be well above, or most of those signals are going to be well above your instrument's self noise, and you don't really have to worry about it that much. But if you're working with nodes, especially if you're used to working with broadbands and not thinking about self noise, and then you move into the world of nodes, it's really important to know the differences, right? So we saw a well-installed broadband seismometer will be pretty close to this low noise model. You can record a range of signals, especially at long periods. Well, the self noise of a nodal seismometer, like say a Fairfield node or the geophone in a Raspberry Shake, is going to have a much higher self noise floor than a broadband instrument, right? So if you plot up one of those PSD curves against the Peterson noise models for a nodal seismometer, this is going to be the lowest noise floor that you can, that you can resolve. You can't reach the Peterson noise models, and especially at long periods, you're going to be well above the high noise model here at periods of 10 seconds and up. But that's okay, as long as you're not trying to do teleseismic surface wave studies with nodes, right? The nodes are carefully selected because you're probably interested in higher frequency signals from more local sources that are going to give you a good clear signal in your frequency range of interest, right? So yeah, it's good to know your limitations, right? If you have a really big signal, long period signal, I have a Raspberry Shake. I've recorded surface waves on it before from very large earthquakes that are in, say, like, Mexico or something. They have to be really big to show up, but they will show up. The broadband station at the lab where I work will record much smaller signals because it's designed to do that. So again, any time you're using data, deploying instruments, know their limitations, right? Pick the right instrument from the job, look at the metadata. Just because geophones and broadbands have the same, BHZ code or HHZ doesn't mean that they can be used in the same kinds of studies. So just be aware of that. Okay, any questions before we move on from that section?
We do have one question. And the question is, in the nominal response library website on IRIS, there exist XML response files for data loggers and sensors. How do you combine those together?
Ooh, good question. I think that's a little more complicated than I want to get into in the lecture right now. But I will say that you could probably do it in ObSpy if you read it in. There's a way to edit the stages in your response. So yeah, that's probably something we could talk about offline, maybe in Slack after the lecture is done. That's all right. Okay. Let's see here. Okay, yeah, good question. Can we use 10 Hertz nodes for surface wave tomography? Well, what's the frequency range of your surface waves? Right? And what, I'm not super familiar with nodes, so I don't know what, the nodes you might be interested in, what their self-noise floor is like. But in general, if it looks something like these Fairfield nodes, unless you have an earthquake source that is, pretty close and going to produce significant long period energy here, I would be wary. If you're talking more like an ambient noise imaging study where you're looking at higher frequency surface waves, say from an active source experiment, well, sure. It all depends on the properties of your specific instrument and the source that you're looking at, right? In general, you want to have a source that's well above 20 or 30 or 40 dB above the self-noise floor of your instrument, right? So if I want to record, teleseismic body waves, this is the accelerometer on a Raspberry Shake 4D. This is only going to record really big earthquakes very close to you. So this is not a suitable instrument. If you want to record very, very small body waves, say as part of a nuclear test monitoring treaty, you need an instrument with a very low noise floor to resolve the smallest signals possible. So yeah, there's no hard and fast rules. It depends. You need to know your equipment and know your specific application for it. Okay, so finally, one last section. I know we're running a little long, but I'm loving the questions, so please keep them coming. Some frequently asked questions about channel naming conventions. And this is finally getting back to that question about orientation and will I have identical metadata for identical sensors? So in general, channel naming conventions, right, the last part of your network station location channel identifier will have 3 letters. And there's it's an easy, or a good reference to interpret these. Iris has this awesome data channels wizard tool. So you can type in the code and it'll tell you, using most standard conventions, what that instrument is and what its sample rate is and things like that. So here's an example, right? If we look at an LHZ channel, I look at this and I say, okay, this is probably a broadband. It's a vertical component and it has a fairly low sample rate. So the convention specified on this website, the first letter is the sample rate. H is used for fairly high sample rate data, again, from a broadband perspective. 80 to several hundred samples per second. B is generally 10 to 80 samples per second. L is pretty much always 1 sample per second. And you'll see V, which is 1 sample every 10 seconds, right? So this is a very low sample rate channel for state of health or normal mode studies or things like that. The second letter in your channel code denotes the type of instrument. So for seismometers, you'll often see H. H is for a high gain seismometer, generally means it's a response proportional to velocity, and N is used very often for data from strong motion accelerometers. There are a number of other second letters, different types of instruments. So if you're working with pressure or infrasound, this would be a B or D, for example. Magnetometers are F, I think. So there's a lot of different geophysical instrumentation that you can get. It's not just seismic. And then finally, the third letter gives you the orientation of this particular channel, right? So you might be used to seeing Z and E, right? And this would be north, east, and vertical. But you might also, especially if you're using data from sites in boreholes, see Z1 and 2. And I'm going to have you think for a minute about why you might want to specify 1 and 2 instead of north and east in your channel code, your metadata. So I'll answer that question in a second. Just think about it for a minute. Okay, another example of an accelerometer of a channel code. This is from an accelerometer based on my second letter. It's a fairly high sample rate. So something in the neighborhood of 100 samples per second. And this one is the one component. So this means, okay, this might be a horizontal. In any case, the person who made this metadata might be using, say, Z12 to describe those channels. General caveat that channel codes have conventions that we use, but they're really guidelines. A lot of channels, especially channels from older data, do not always respect these exact definitions laid out on these slides and in that really nice data channel wizard. So when in doubt, inspect the response, right? The response will tell you your sample rate. The response will tell you what kind of instrument you have there. So data channels can be useful for getting an idea of what's there, but exceptions exist and you should always be careful about that, especially if you're working with data from networks that you don't know well. Okay, so to get back and answer that that channel naming conventions question. So why would you possibly want to use Z1 and 2 instead of like, well, let's just put my seismometer down and we'll align it to north and we'll call it north, right? Surely that's the most simple way of doing this. Well, there's a couple different reasons that might not be suitable. Many seismic stations are deployed in situations where you can't orient them precisely to true north, right? So if you have a station down a borehole or a post hole that's tens of meters or hundreds of meters deep, by the time that instrument gets lowered all the way down, you don't really have a good way to precisely align that station with true north, right? If you're doing an ocean bottom seismometer deployment, you throw it off the edge of the boat, it lands in an orientation, but you do not have a good way of aligning that to true north, right? So in that case, those are situations where you have to measure the orientation of the seismometer afterwards. And there are various techniques to do this. I won't get into that here, but one way you do that is, or in general, you have an instrument with a known orientation as your reference, and then you can calculate a relative orientation of your unknown seismometer. Another reason you might want to use Z1 and 2 instead of Z north and east is that sometimes seismometers are installed despite your best efforts with an incorrect orientation. So during my PhD, I installed a seismometer. We're using a magnetic compass. Our seismometer had a nice little north line on the handle. And I aligned this thing beautifully, like these two lines were perfectly parallel. But we discovered after processing the initial round of data that I had installed the seismometer pointed south instead of north. And fortunately, it was easy to fix. We just changed the orientation in the metadata. So instead of saying this component is pointed at 0, this component is pointed at 90, we just said, okay, this one's at 180, that one's at 270. It was very easy to correct for in processing once the error was known. This is something we do all the time. Installation techniques have improved over time. We get better estimates of orientations. And so if you use these horizontal names 1 and 2, people have to go look for the metadata. You have to use the orientation. And that's just a better way to do it, because then you're not encouraging people to assume that all of your instruments are pointed north and east. So this is a convention that is used very widely at, say, the GSN, for example, since we have a lot of borehole seismometers. Okay. Yeah, and if, again, if you want some details on digging into the orientations of the transportable array network, you can check out these 2 papers assessing how well those stations are oriented. Okay, so that is the end of my lecture. I see we have one question. I'll get to that in a second. Please go ahead and ask any questions about the lecture, because what I'm going to do next is say, go ahead and open up the IPython notebook and explore. I'll be here to answer questions. But really, I encourage you to just run that notebook and then try changing filtering parameters. Try changing the response removal parameters. Just check it out, experiment for yourself. This is very open-ended. I don't have a target answer for you in mind. I just want you to explore and see what you can do and see how different options affect the outcome. Feel free to obtain data from your favorite station of choice. Put in deconvolution parameters that are relevant to you. And yeah, check it out. And then if you want to do some homework, you can go to the OBSPy tutorial and you can produce those PSD PDF plots with the high and low noise models and the rainbow colors. You can compute those for any station of interest. That if you have data for it locally, or you can obtain data from it somewhere, you can produce your own PSD PDF. So that's what I encourage you to do.
Okay, yeah, it looks like we have a couple of questions coming in. So first question is on terminology. Are station corrections the general term for correcting for noise and or response like we've been talking about, or is that something different?
Well, so the first thing that I think of when I hear station corrections is like, say a correction when you're doing body wave tomography. I think, like for a local or for an arrival time of a seismic phase, accounting for local structure. So that would be something different. I'm not sure what the exact application of that, or what that the context of that station correction term is, but I believe, at least the way I usually hear it, it's something different.
Okay, and then the second question is, how do I get metadata for a data stream that's in mini-seed format?
Okay. So yeah, assuming you already have your, I'm assuming this is waveform data in mini-seed, right? You should know the network station location channel of that data, and you can request it from the data center that provided that same waveform data. Right, so if you got your data from Iris, they won't serve you data, waveform data that they don't have metadata for. So you would go back to Iris and request the metadata for that station.
Okay, great. And so our next question is, if we collect data from a high sampling seismometer with a sampling rate of 50 Hertz, and we downsample it by resampling to 5 Hertz, will that data be the same as something that was recorded by a low sampling seismometer of 5 Hertz? Mainly the question is if there are effects of instrument properties on the data collected.
Okay, let's see here. So I will say in principle, no, right? If you have the same seismometer, let's say an STS2 broadband seismometer, recording at 50 Hertz and you downsample it to 5 Hertz versus just recording at 5 Hertz initially, if you are close to the Nyquist frequency, right? So if you're like a Hertz or more for that 5 Hertz data stream, right, 2.5 Hertz and then about 50% of that, it'll be different, right? Because that decimation process and the anti-aliasing filters that you're using, that'll make a difference. At long periods, in principle, no. I do want to point out, because this is something that is not always clear from the way we talk about things, that we might talk about 120-second seismometer, right? And that means a seismometer with a corner frequency of 120 seconds versus say, a 1 Hertz geophone, right? With a corner frequency of 1 Hertz, 1 second, right? Those two instruments, right, will have a very, very different response. And they will not look the same if you just downsample those two streams, right? So the sample rate of an instrument is very different from its corner frequency, right? You can take a STS2 with a corner frequency of 120 seconds. You can sample that at any rate you want. That's not what changes the response of the instrument. That corner frequency is an electromechanical property of the sensor.
Okay, awesome. I'll just see if we have any other questions trickle in. And I'm thinking, do we want to take a 5-minute break and let folks pull up the lab and, you know, get themselves situated?
Yeah, I think so. And I don't really have a, I mean, do you want me to run through the lab kind of on video, or let folks go? I can do either. If people have preferences, but yeah. So I'm gonna say go ahead and let's have everyone kind of work through this themselves, and I'll be here and on Slack for questions in the metadata unit 1 area.
Okay, and I think given that, I think I'm going to stop our recording just so we don't have 45 minutes of you sitting
staring at my screen. All right.
Cool, that sounds good. And yeah, I'd say everyone take a few minutes, download the, pull everything from GitHub if you haven't already, and start working through this lab, and feel free to direct questions either in the chat here or on Slack. And we'll probably go for about half an hour.
Sounds good.
Okay.
Okay, cool. Yeah, thanks everyone for your questions.